Hey guys, we're going to jump right into some performance checks now that the geometrics of the roundabout are kind of laid out. And I'm just going to try and trim this down in terms of time as much as I can. So, getting right into it. The very first thing that I would probably do on this in terms of my performance checks would be to run auto turn. Those are going to be the easiest tweaks, and you always need to design, accommodate for that design vehicle in terms of some of those thresholds. So that would probably be the first thing, and then I would go to my fastest path calcs after that, because those two things are going to be competing against each other to some extent, and you really want to balance both of them out. So right off the bat, I do have auto turn loaded. I'm not going to run it. I already ran some of them, but there's a cool tool in here you can get it to if you guys don't have auto turn. There's also other programs you can use to do the same thing, but having it here is pretty nice. So you can select the vehicle you want, generate a path. Right now I have the WB67, that's our design vehicle, and I can generate paths and place this guy and do some cool things with it and run through my roundabout. I already have these kind of done, so I'm just going to turn them on and show you really quick what that looks like in terms of the leveling. I really like to make my own levels on here. Just helps, maybe eventually MDOT will put it in the workspace, but for now I just like to use this level manager. I'll make my own levels for some of these design checks just so they're easily turned on. So I'll show you this truck turning movements left, and then I'll color code them depending. So that way if we ever do exhibits and stuff like that, which I like to include in our geometric memo, they're easily, turn on your print with color and use the pen table and stuff like that. You can really clearly see those truck movements going through. So this one's a left movement. If I turn on my pavement marking lines in here, you can kind of see this chevron area. The truck is allowed to use that chevron area as it enters. That's just based on a case operations that you can find that we ended up going with a case 2. As it goes around, this is the truck apron that it's kind of using, and I'm kind of holding to that lane line here, going through and taking my left turn. And you can see like there's some pretty tight spots, like on this one, we're pretty much on the edge line on each side coming through that curve. So that's a good sign. This, I think originally the very first time I ran through this wasn't the case, and I needed to widen out this entrance a little bit based on some of my turning movements. So that would be something where you would tweak. You could take those do not construct lines, move them out, change the radius a little bit, widen it out, and just kind of go through and play with those iterations until you get something that works. So, I have truck turning movements for pretty much every movement in here that I think are all look pretty solid. So I have a through, I have a left. I have actually 2 throughs just because I wanted to make sure that my through on the inside part of the lane still worked as well. So that covers those. And once those are good, then I like going to my fastest path calcs. And those you can lay out. NCHRP has some pretty good guidance on that, but it's not super thorough. So I'm going to try and go through some of that for you. So the very beginning, I like to again make a new level, call it the fastest path level. There's a bunch of information that I'll try and go through, but NCHRP kind of covers this whole section, and the MDOT roundabout aid also kind of just takes some information from there and pastes it into here. But overall, there's some thresholds that you have to meet in terms of fastest path, and this is what's going to compete against your design vehicle. So the very first thing that I like doing, it shows in NCHRP offsets from pavement lines being, I believe it's 3 feet, and then offsets from the front of curb being 5 feet. So right here, all I did is I created this fastest path level. I came through and I took some offsets of 3 feet off of my pavement marking line, and then once I got into the splitter island area, I just did 3.5 feet off of my edge line, because these back of curb, basically the B2 curb is 1.5 feet from that edge line to the face. So 3.5 feet, that is 5 feet off of the face of the curb. And these are basically going to be where the center of a vehicle could theoretically be in terms of taking that fastest movement. And in this, all pavement markings are ignored. So this is just how fast could a vehicle theoretically come through this if there was no other vehicles and pavement markings were ignored. And that's going to be determined based on the radii that you're getting from these sections. So this first line, this first circle, at a minimum, they would like you to start your kind of your B-spline curve for these radii and these movements 165 feet out from the entrance of basically your ICD. So that's kind of what this first one is set out. It's 165 feet. Obviously on this side, it's a little bit longer. When it comes to the offset, this ends up being 255 because this is a 180 foot ICD, so you got the 90 feet. So I offset that out from the center, 255 feet, and that meets those requirements. And then I did another 75 feet back from there and another 25 feet back from that one. And these are really just going to hold kind of my points before I enter into this. So with that, you want to I kind of make up another level. I have a right and a through. When it comes to the left, we'll kind of get into that later, but you don't really need the left too much. It's not very important because it really is just based off of whatever your central island radius is. But for this through, that's kind of the most important. You're going to get the first 3 velocities off of the through fastest path movement. So I kind of have these mapped out here. I'll trace in on this one. And this is just created using this B-spline. If I can find it right here, this B-spline by points. The first 2 points I select on the intersection of that line for my outer edges, and then after that, these basically these 4 points afterwards can kind of change a little bit to kind of figure out where that these 3 points can change to figure out where that tightest radius is. So from that, you're going from the inside, and then if you're thinking just logically, if you're trying to run through this, you're going to drift essentially over in here. That's what this point is used for, so you can adjust this point, and that'll kind of move that back and forth. But really, I want it to be as close to this guideline as I can, because that's going to give me that radius, that flattest radius, and that theoretical speed. Same thing on this point. You can take this and move it, and that does change the whole spline. So you'll have to go back through and kind of reiterate, but you want these to kind of be as close as possible. For this R3. Exit movement, it doesn't necessarily have to be in this place, especially for a 2-lane. This basically, if there was a circle here, this curve would be so flat. The calculated speed would be through the roof because it would be based on that radius that you have, which is really flat, really high. So that could be a really high speed here. But the thing is theoretical speed is kind of what's more important in this situation, because they're going to have to go around this curve here, and that's going to slow them down to a certain speed. And really the question is, how fast can they accelerate from this speed to this point of interest, which would be that crosswalk. So that's really going to be your V3 speed. It's not going to be calculated, but really a theoretical acceleration point, and we'll kind of get into how that's mapped out. But so right here, the guidance kind of shows in NCHRP, it talks about basically this R1 value should be measured over a distance of 65 to 80 feet. And it is the minimum radius that occurs along that. So when I'm mapping these out, I just create a circle. This is a 70-foot, so 35-foot radius, I believe. And now I just know when I'm putting in my line for my radius that I'm trying to determine, I just attach on to whatever after I get this to be my best fit B-spline, I'll attach on to those, and then, I know this length then is 70 feet, and then in terms of the area, I can move this left or right, but really it's probably going to land in this area somewhere. And I just try and find kind of that smallest radius that I can get out of that while holding true to this B-spline. So this one I typed in as R1 equals 267. You can see right here, my radius on that 266.23. So Same thing on these. I just kind of place these circles around where it's tying into that guideline the most. And then this one I do not do for V3 because it's going to be calculated off of this V2. So from this, I like to create an Excel spreadsheet and kind of include this in the geometric memo that kind of maps out all of our geometric, thresholds and then what our values are. So in here, I have some information from NCHRP just for my own sake, but really this table is kind of what I like to include in the geometric memo. And this kind of goes over your entry widths, and it kind of gives a standard, and these are from NCHRP or the MDOT Roundabout guide. The reason for this being so different in width is that I have a single lane and a double. So a lot of these are like, the east and west leg are both going to go by the double guidelines, the multi-lane roundabout guidelines, and the north and south leg need to go by the other single lane guidelines. So I do highlight what is out of standard, and we can go over some of those, but typically you're never really going to get this whole thing to be green, especially the entry angle, and these R5s typically can be pretty difficult. But you can see in here, I have my 267 radius in, and then this is just a calculation based off of that radius, what that theoretical speed would be. So we're at 29.8 miles per hour. The threshold is 20 to 30. It's really 25 to 30 for multi-lane and 20 to 25 for single lane. So green, we're within the threshold, but we're on the higher end of that spectrum. But this combined with knowing that my design vehicle is getting through, and it's getting through pretty tightly. Like I don't have a lot of space there. If I try and bring this speed down anymore, I'm going to put more curvature into my roundabout, and that's going to negatively affect my ability to get my design vehicle to go through there, which I already know is also tight. So it's a competing objective between these two, and I think we can argue the point in terms of geometrics that we're meeting both, the design vehicle very closely, getting through the roundabout, and still the speed, even though it's on the higher end. And then this 172 going to that R2 value, it's done the same way. And then that gets me to the V3 speed, which is, again, kind of, it's based on this D2-3 distance. And that's kind of your distance between, and I have a level for that too, to show. It's really the distance between the center of this, your R2 value, and then your point of interest. And our point of interest in most cases is going to be a pedestrian crossing. So it's how fast can a vehicle speed up from this velocity to this point if they needed to hit the brakes and they saw someone crossing or something. So I kind of mapped that out with a B-spline, just following my movement there, and I got a distance of 131 feet. And in here then you can do another calculation which includes that 131 feet along with your V2 speed. And the threshold for this just needs to be within 15 miles per hour of your V2. So like in this instance, if we added 15, we'd be at 37.9. So we're under 37.9. We're on the higher end, but a lot of that has to do with the fact that we wanted the hawk signal in here, so we had to offset this, which increases that D2-3 distance. So keep that in mind. The farther you offset this, the more issues you might run into. So even the offset here, we want 2 vehicles to fit in, but if we keep going back and we expand that to like 4 vehicles, we're going to have an issue on that crossing for that speed. So try to move past it a little bit, go into that R4. This one's really simple. It's just going to end up being whatever your offset is on your central island. So this is a 63.5 foot radius on this offset of 3.5 feet off. So I just rounded it up 64 because as you're going left, you don't even need to really map this out because this is going to end up just matching that curve exactly. And then for the R5s, these we did have some issues with. And it mainly comes down to the distance between these 2 legs. So like this one here, was pretty tight just because this exit is up higher, this entrance coming in, you get some pretty good curvature off that. But on this one and this leg down here, you can kind of just tell some of the issues like might be that this ends up being a pretty flat curve going around. And this competes again directly with, if we check our right movements for these turns, I'm pretty tight like on this purple getting in, so I can't really do too much in terms of changing the curvature. This is kind of where it's at. An option to help with both of these would be to widen out this splitter island and push this farther out here, and that way you could get a tighter radius on this. The issue with that is kind of going back to this footprint that we have and not wanting to take up right away. There's some houses and stuff like that hidden in here, so we really wanted to keep this tight. So you do want to highlight these things when you're writing your geometric memo. You want to highlight, you don't want to run away from them. You understand, like, they're going to understand that there are going to be sacrifices that need to be made. As long as you can justify them, and you're still within, pretty close threshold to those standards, then geometrics is going to understand, and you just need to relay that information to them. So if we wanted to fix those R5 values and those entry angles, which we'll get into in a little bit, I would say that the issue, what we would end up having to do is really widen this splitter island out and push this exit farther out here. And the same thing kind of down on this one, this exit, is going to have to end up being out here. And that's just not necessarily feasible, especially in this quadrant, based on right-of-way impacts and just the overall cost and things like that. And if you look at the threshold, it's 20 miles an hour threshold. We're not too far ahead on these. So I'm going to highlight this, but I'm going to give them the option of, in the geometric memo, of what we could do to get those to fit, but ultimately recommend against that because of the cost and like, honestly, this roundabout probably wouldn't even get constructed on that, just simply because of the right-of-way take that would be required. So those are some of the things you want to highlight and justify when you're writing out your geometric memo. Again, don't run from it, because they'll know that it's there when they see the fastest path calc. So that gets me kind of like to one of the last. There's some other ones, like you want to do your path overlap, but really those first two, the truck turning movements and your design speed, those are going to be competing objectives that are probably the most important. And then after that, you have some other considerations that you want to do checks on, path overlap being one of them for multi-lane roundabouts, and entry angle and sight distance is obviously another one. I never really have an issue with sight distance, so I keep that one kind of for the end. I do that check, but if I can get the fastest path and design vehicle accommodated, I know I'm probably in pretty good shape. And then this is kind of that third one that I'll run, which is the entry angles. And I'll create a level for this, and I'll just show you kind of how I create the entry angles really quick. So this is talked about in the MDOT roundabout guide, but I will just kind of quickly run through. I'll set three lines along my curve, perpendicular to that curve, one in the middle, one at the end, and they don't have to be perfect. I typically come out with the same answer even if I do this multiple times. So excuse me. From here, I'll trim these back to be the exact width of my roadway, and then I'll take a curve and I'll just do a center, start, end, and get on this snap. And I'll put a curve in here, and I'll snap to the very centers of those, and that's kind of my center curve. And I'll do the same thing for the exit here. You expand that curve out to what would be the front face of your curb. This one's a little goofy because I have two different ICDs kind of going on, so I'm kind of going off of this to start. And then you want a tangent from this point, so I'll do a line from element. Now that that's squared away, and right from that point, and then I'm just going to shoot. And sometimes it goes backwards, just depending on the curve direction, but not a big deal. You can just take this and reverse it. So I'll do one of those, and then from there you want the angle in between that these cross. So I'll just take really quick, if I can find it. this one, and I'll just take an angle between these two lines. So that's giving me 41 degrees, 7 minutes, and 14 seconds. From there, you can convert that angle. If your two legs if they're farther, basically if you had a 3-leg roundabout and this one didn't exist, then this entry angle can just be your phi. But if there is another leg right next to it that's within 100 feet, it's phi divided by 2. So really you're going to take this angle and you'll divide that by 2 to get your entry angle. So that's kind of shown in this calc up here in these. That one was this one, so 41 degrees, 7 minutes, and I think I had 29 seconds the last time I did it, so slightly off, but not too far. And then that gets calculated, divide that by 2, and that gives us 20.6 degrees. And we want these to be between 20 and 40. I almost never get all of them to fit. So, and really this and your R5 are kind of tied together, and really, like, again, this is in direct competition of your your design vehicle needs. So if we wanted to improve these and get those up to 20, this angle essentially is going to have to come out. This entrance or this exit is going to have to. This one's actually good. So if we were talking about one that was bad, this one would have to come out here to get that to fit. And again, that's just not necessarily feasible. And I think it's something that geometrics can live with, and you just need to make that argument in the geometric memo. So yeah, from there, at that point, once you kind of get everything laid out and you've tweaked it to the point where you feel pretty comfortable, this one we had to do some path overlap because it is a 2-lane in some of the sections. I'll add in some other information that might be helpful to them. This is also information that helps in terms of Rodel, and then I would create my roundabout memo. And in here, you're just really mapping out everything that you want to go over. So we kind of introduce everything, the planning level operations. This is where we're going to get how many lanes and capacity that we need, and kind of the upfront Rodel information. And then from here, I'll put in my design considerations, kind of everything that I've talked about in the previous video, that ICD, why we chose 180 feet, and why we chose to put the alignment and place it in the location that we did. I'll show some alignment of the approaches, just to kind of give you an idea of where they're coming in at. Angle between approaches, talk about the splitter islands, entry width, circulatory width, central island, entry design and exit design, what those widths are, design vehicle considerations, what our truck apron is, potential right-of-way impacts that we can kind of hit right off the bat. And then I'll show my performance calcs, and this is kind of where that table comes in. And I'll highlight, some of these are just the fastest paths. So like I'll highlight these and then justify why these need to get updated. This is from previous submittal. But why these are still going to be okay and the best option. And then, we'll hit some of those other sight distance, angles of visibility, entry angle. Get into our design details, and then kind of we talk about the vertical considerations, but we don't really get into it yet until that preliminary submittal where we'll start modeling the 3D geometrics of it. But we'll just highlight some things that we see. And then from there, we'll do a designed operational analysis where we take the information from this roundabout and we'll put it back into Rodel and we'll see how it operates, and we'll talk about that. But yeah, that's kind of the gist of some of those fastest path and performance checks that you have to go through. And it is, you'll get very good and quick at doing them because it is an iterative process. So you go, you do the design vehicle, you run through auto turn, you're tweaking things, you get the auto turn to fit, you turn off those levels, and then you go check your fastest path, and then you do that, and you're like, okay, this is off, and now I gotta change my angles for fastest path. And then you have to go back and do the truck turning movements again because that changed your geometry. And then really you're just looking for the balance between getting your fastest path, calcs to be reasonable and and doable, and getting your truck turning movements to obviously meet the requirements there. And once you have that, checking entry angles, and visibility and things like that. So yeah, hope that helped. Hope it wasn't too long. I know it was too long, but see ya.